to my lecture today. Can you all hear me clearly, right? Okay. So once again, I want to welcome you to my lecture today. Of course, today the focus is going to be on multiple comparisons. I think I need to have a recap. So how do we find ourselves in a situation where we need to apply multiple comparisons? I think the story actually started, using analysis of variance technique, to compare means in more than two populations. And of course, we know we got two hypotheses in the research. Of course, the non-hypothesis is basically going to say the means are the same in different groups. While the alternative is going to say at least there's a difference in a particular peer. And I told you the other time that we have a contrast when we are actually applying statistical technique ANOVA in trying to investigate whether different exists. Now the first contrast is the plan one. Okay, the plan one, before you go into experimentation, before you conduct ANOVA at all, maybe based on your experience, of course, you've already figured out, the levels of independent variable that you basically are going to compare. Of course, we call that a planned contrast. And of course, that was what we handled last week, where we assign, we need to assign weight. Okay. And of course, I walk you through the statistical method of doing that, ensuring the weight are orthogonal, and so on like that. And I also said we have other contrast, and that very contrast is not a planned one. That very contrast is what we call a post hoc contrast. And the only condition under which we consider the post hoc contrast is when we've already performed experiment, we've conducted analysis of variance, and of course the non-hypothesis has already been rejected. Maybe when you compare the p-value associated with the test, you realize that the p-value was less than a reasonable level of significance. You reject the non-hypothesis. And when you reject the non-hypothesis, one of the disadvantages of ANOVA cannot help you to figure out where the difference lies. I'm going to say that again. The analysis of variance will not tell you where the difference lies, but the only thing the analysis of variance is going to tell you is either difference exists or not, but it will never tell you where the difference lies. And the only way to know is when we actually go through today's topic that we call multiple comparisons. So the multiple comparison that we want to do today is a post hoc test, post hoc contrast test, which means we've already taken a decision of rejecting the non-hypothesis. And of course, we want to investigate further where the difference lies. And that is why we need what we want to do today. But let me tell you this. We got different methods. When we want to do multiple comparisons, and these methods, they have error implication. Some methods in multiple comparisons, some are liberal, some are conservative. For those of you in the United States, of course, there are two major parties in the US, right? You have the Republican, you have the Democrat. The American public don't really want a situation whereby the Democrats will actually be, total liberal. They don't want a situation where Republican will be highly conservative, because if Democrat is highly liberal and the Republican is highly conservative, of course, it may be difficult to pass a bill, on about, partisan level. And that is the reason. So what I'm trying to tell you now, under the multiple comparison test, there are some of them that are too liberal. There are some of them that are too conservative. What do I mean by too liberal? What do I mean by too conservative? When a comparison test is too liberal, it means even if difference doesn't exist, it's basically going to dictate a difference. That means it's too liberal. When a multiple comparison terms is too conservative, it means even if difference exists, it will not dictate that. So what I want to present to you today, presenting some methods, other multiple comparison tests, some that are liberal, more liberal, some that are more conservative, and some that actually, that find ourselves in the middle, moderate, just like the way you have moderate Republican, moderate Democrats, or for those of you who are not from the United States, where you practice a political system where you have the right, you have the left. You don't want a situation where the both sides go to the far, either far right or far left. You want something in the middle. This is just, the summary of what we want to do today. I will now be able to tell you which particular multiple comparison test is appropriate for a given situation based on what you've heard about. Now, because of that, we're going to consider error rate. Of course, comparing multiple comparison tests, we're basically going to compare them based on the error rate. Don't forget, we live in a world, we want to capture the world, but the fact remains, the model we're using cannot capture the world exactly. And the only way to tell if a model performs is to compare the error of that model with the other model. And of course, you're going to have different kind of multiple comparison tests. Now, take a look at what I'm showing you now. The very first thing is for first figure out what is the possible number of multiple comparison tests I'm actually going to have after the null hypothesis has been rejected. If G represents the numbers of groups, don't forget, the multiple comparison test is like testing two groups at a time. Testing two groups at a time is what we call a pairwise comparison test. If I want to know the possible numbers of pairwise comparison tests I want to conduct, then I will go combinatorial analysis. And that's why you see G combination 2. Why 2? Because I only want to compare two groups at a time. Therefore, K will be equal to G combination 2. That very K will be the number of possible pairwise comparison tests. Okay, and of course, the numbers of hypotheses you're going to have will be K. But let me tell you this, the moment one hypothesis is rejected out of the K number of hypotheses, then we're actually going to assume that we're going to reject the whole hypothesis the moment we find one that is significant. Because don't forget, what we were targeting before is to identify where the difference lies. Okay, now some of you may be wondering, why not using the conventional t-test? I told you from day one, using the conventional t-test, the type 1 error will be inflated. And I'm going to demonstrate to you today how type 1 error can be inflated. And some of you, I know you've been wondering why, when do we normally reject where p-value is less than alpha? What is alpha? The alpha is a level of significance. The level of significance, I also call it a level of statistical error. The level of statistical error, it is also the maximum probability, of committing type 1 error. Let me tell you this. What do I mean by type 1 error? The type 1 error, is rejecting the non-hypothesis when it is true. When there is no difference and you say there's a difference, that's a false positive. And let me tell you, our research is not error-free. When you are assuming alpha to be 5%, you know what you mean? It means if you conduct 100 tests, right? Even though the non-hypothesis is true, I'm going to say that again. If you conduct 100 tests, even though the non-hypothesis is true, when the non-hypothesis is true, what does that mean? When our hypothesis is true, means you shouldn't reject. But let me tell you, the type 1 error, 5 out of the 100 we reject. We already acknowledge that because our model cannot give us exact reality. And that is the reason why, as a researcher, we need to, show the world at the beginning of our research the error we can tolerate, which is 5%. That's why we always give a standard of 5%, which means my research has a tendency of misleading the world 5 times out of 100. And what does that mean? It means the probability of actually taking the right decision, right, will be 95%. Like, in 95 out of the 100, if the H0 is true, it's going to say so. It's going to say yes, H0 is true. But 5 out of that 100 is going to say no. And that was the reason why the p-value you always compute is the probability of observing an extreme value when H0 is true. When that probability is less than alpha, that is where you normally reject. When it is greater than alpha, you fail to reject. Okay. Now, the reason why you cannot use conventional t-test for pairwise comparison is because the type 1 error rate will be inflated. How do I know? In one test, if the probability is, if I use alpha for one test, it means 1 minus alpha will be a correct decision, right? If I raise it to power number of the test, right? Now, the probability, okay, the probability now of at least, taking correct, at least, that you're actually going to reject the non-hypothesis when it is true, is going to be 1 minus this guy. Now, let's see. When k equal to 1, if you plug in 1, what are you going to have? You're going to have alpha mathematically. But when k equal to 2, when the number of hypotheses is more than 1, this guy is no longer going to be alpha. It will be more than alpha, mathematically speaking. If you plug in 2 here, and maybe you assume alpha to be 0.05, okay, if you put 0.05 here and k equal to 2, the result you're going to have will be more than 0.05, which means that type 1 error has been inflated. Therefore, we need multiple comparison tests as against the conventional t-test. Okay, that's exactly what I'm trying to show you now. Now, of course, this is the error rate that I talk about. Nature knows the truth. We normally take a decision. It is not all decisions that we take that are right. What I'm displaying to you now, when you reject HO and when HO is true, that's a type 1 error. But when you reject HO and HO is false, that's a correct decision. Okay, when you fail to reject HO, when HO is true, you fail to reject, that's a correct decision. But when you fail to reject HO when HO is false, that's a type 2 error. We commit this all the time. But it becomes more problematic when you are conducting a multiple comparison test, where you're actually going to perform more than one test. And what I'm trying to show you now is that's A, B, C, and D. Of course, when you add them up, that would be equal to K. That would be the totality of the number of comparison tests that you conducted, out of which you take wrong decision. That's exactly what I'm trying to say. Now, I told you the other time, we've already ruled out the conventional t-test. We basically want to consider multiple comparison tests, but the multiple comparison tests, some of them are liberal, just like what I said when I started, and some of them are conservative. And that is the reason why, based on the error rate, okay, we're basically going to, I'm going to, tell you in this course how, the appropriate one that can be used. Give me 1 second. Is there anyone want to ask question based on what I've said? Is there anyone? You like it? Okay, go ahead. Somebody want to ask question? Okay. You everybody is good, right? Okay, you like the story, right? It's a story. Okay, now we're actually going to consider, want to talk about the types of error rates that we have. The very first one is, and that was why I said you need to decide which error rate to control, then select the statistical procedure that control for the error rate. But let me tell you this, there is something that is technical. Reason why multiple comparison actually have error rates in the first place, because of the fact that, I'm gonna write something now. Okay. For instance, you are comparing ABC, you're comparing 3 groups, A, B, and C. Do you know there are times when you test, when you are testing that mu A equal to mu B equal to mu C, and under the at least one is not true. Okay, if you reject this guy and you are here now, you actually consider multiple comparison tests. Okay, do you know that maybe there's no difference between this guy? There's no difference between this guy, but the difference exists is between this guy. I want you to take a look at what I wrote on the board. That is against mathematical rule. Can somebody tell me, why is it that this guy here, for extra credits, is against mathematical rule? Can somebody tell me? I'm going to explain this again. You're comparing 3 groups, right? And you've rejected the null hypothesis, right? Because your p-value, maybe your p-value is less than alpha, and you basically want to compare comparison, test, you're going to do this. Maybe you realize that this is equal, and the difference lies here, but I'm now putting it to you that this is against mathematical rule. Can somebody tell me why it is against mathematical rule? Oh, good job. You just said it now. Send me a message for extra credit. The guy online. Look at me. Can you see me? Good job. You just tell me the reason now. Send me a message for extra credit. Somebody just gave me the results, but I also want to hear from you. Why? Why is he against mathematical rule? It's against mathematical rule because if A equal to B, B equal to C, A should be equal to C. Does that make sense? That is why this is against mathematical rule. But do you know why? This against mathematical rule, because don't forget, in statistics we use sample. We did not use everybody in the population. And do you know what will make our result to be great is when we consider large sample. When you consider large sample, you're very close to the truth. Most of the time, we're limited by budget. Okay, now the different kind of error rates that we have. Number one is what we call POS error rate. That is the uncorrected one. When you use a conventional t-test, if you have more than one test and you still use 0.05, you are not using the 0.05. What you are using is more than 0.05 because it will be inflated. The second one. And that kind of test is what we call the LSD, what we call the least significance different test. Now we have what we call family-wise error rates. Why do we call, what is family? Oh, this is a family. This is another family. This is another family. The numbers of, each peer that you are comparing represent a family, and in each of the family, they got their own error rates. You cannot use the same error rate for all the families. When you do, then the error rate will be inflated, it will be inflated. The type 1 error will be inflated, and you're basically going to mislead the general public. And therefore, we need to protect the LSD. And that's what we call, protecting the LSD. Okay. Now, another one is what we call false discovery rates. I told you, some multiple comparison are liberal, some are conservative. Those that are liberal, okay, they will return a lot of significant results, even if the H0 is true. That means they are too liberal, and then we have very huge false discovery rates. And that's why at times you see researchers celebrating, oh, we've got it, we've made it, we've done it. Even though the null hypothesis is not supposed to be rejected, because the multiple comparison technique they are using is too liberal. It's too liberal. There will be a lot of false discovery rates. We have so many examples of such there, like Benjamin, home test, and the like. Another one is what we call the strong family error rates. This is nice because, Turkey, Bonferroni, okay, that are very, very popular, Scelfie, they are in this, because look at that, strong family error rate, it means an adjustment has been made. I'm actually going to tell you the difference between the Bonferroni and the Turkey. I'm actually going to, let me start with the Turkey. The Turkey is based on studentized range distribution. Okay, Turkey is based on studentized. Watch out. This is part of the exam. If you remember, as part of, if you look at the midterm practice question that you have, they ask about this, right? Turkey is based on studentized range distribution, and it is used for balanced design. What do I mean by balanced design? When you have equal numbers in each group, just like the sandwich example that I walked you through the other time, right? Where we have 8 in each group. Okay. And let me tell you this. If you really want Turkey to do well, okay, you basically need to use, a very moderate sample size. A moderate sample size or a large sample size will lead to huge statistical power. Don't forget, when you use a huge sample size, right, what will happen to the standard error? The standard error will be very small. Don't forget this. Do you remember that? Right? When the sample size is large, this guy will be very, very small. And when the standard error is very small, what is going to happen in your test? You are more likely to reject the null hypothesis, because your statistic will be very high. When your statistic value is high, you know what happened? Your p-value will be small. When p-value is small, that is going to point towards significance. Okay. So, but one thing with Turkey is not appropriate when you are working with unbalanced design. What do I mean by unbalanced design? When the number in each group is not the same. But somebody called Kramer adjusted Turkey. Okay, we now call that Turkey Kramer. Okay, if you go to textbook, you're going to see Turkey Kramer. I think Turkey should be TU. Turkey Kramer. The Turkey Kramer is used for unbalance. But the conventional Turkey, this Turkey here is what we call honestly. It's the same thing as we also call it, honestly, honestly significant difference. You know, what is it trying to say? The significant difference that you get is you are being honest. That is a meaning, because the Turkey has already been adjusted, right? To withstand, to control the family-wise error rates. Any question on that? Now, when do we actually, what do we actually see as, advantage of Turkey? Turkey is a generous method and can be used to detect, difference during pairwise comparison, and it's less conservative. When you say less conservative, when it is too conservative, it means it will not return the significant effect, even if significant difference exists. Okay. And to avoid the illogical result, the illogical result is when A equal to B and B equal to C. If you really want to have this, where this equal to this and this equal to this imply, if you want to get this, then it means you need a adequate sample size. Adequate sample size will lead to strong statistical power. Okay, so that is what we actually mean. Now, the next one is Benferroni. Okay, so when do we use Benferroni? Okay, of course, the idea behind it, Benferroni is used most of the time in clinical trials. Okay, and it is not only used for ANOVA, it also used in the variants of ANOVA, like analysis of covariance, and so on and the like. And it is based on T distribution. Benferroni is based on T distribution. Okay, and it is more rigorous than Turkey test. Okay, and more rigorous than Turkey test, and more generous than the very conservative SCEFI. Those are the particular comparison test we're still going to talk about. Is highly conservative. Okay, so we should call SCEFI. Okay, and the disadvantage of Benferroni is just unnecessary conservatism. Conservative. What make Benferroni conservative is because it has a weak statistical power. What do we do in Benferroni? You divide your level of significance by the number of tests. What happened? When I have when I have phi equal to 0.05 and I have k equal to 100, do you know what Benferroni is suggesting? Use this to determine your new level of significance. What will happen here? Your new level of significance will be very, very small when k is large. When your p value is very, very small, when k is large, it may be difficult to have a significant result. I'm going to say that again. When your p value is extremely small, don't forget, for you to reject, your p value has to be less than alpha. But what if the alpha is very, very small? It may be difficult. And that is a disadvantage of Benferroni, which means in a way kind of conservative. Okay, another test, because before I'll start showing you because you need to understand the nitty-gritty. There's another test that we call donut. Donut. Do you know when we use donut? Donut is very, very useful when you are not just you are not considering all the possible comparison tests, but you are only comparing control with the other level. I'm going to say that again. We use donut. Donut is a very good multiple comparison test when you only want to compare control with the other level. You know, in some research, you have control, right? And you have some levels of treatments. An example of such research, maybe you consider in dose, right? Is 0 dose, 2, 4, 6. Now, if you're comparing this with 2, comparing this with 4, comparing that with 6, we use donuts. It's a very good comparison test. Then the last one I'm going to talk about before I actually show you what I have on the slide is what we call SCEFI. We use SCEFI when you are working with a snoping data. Snoping. What do you mean by snoping? You know, I normally experience this when I was in Africa. You know, in Africa, when I was doing my PhD, some companies will come to me and they're going to tell me, they're going to say, Kazim, we want to make it as if to look to government that we're really doing a great job. Can you make our results significant? Which means they are trying to tell me I should fabricate significant results for them. We have a way that we do that in statistics, but that is not good because you want to mislead the public. You know, snoping, the idea of snoping is when you artificially fabricate a difference, even though difference does not exist. I'm going to say that again. We have some data like that. We have a way to do that. And that is why you shouldn't be at the mercy of statisticians. And that's why you need to really, for those of you who are not in statistics, you don't just depend on statisticians all the time on the results. You also need to have an average knowledge of what is going on behind the scene. Because you know what? We got method that can fabricate false results. That will look, and that's what they're going to present to government. Oh, we're doing a great job. And if I want to control that, you know what I'm going to do? I need highly conservative method. You know why I need highly conservative method? Because the way the data is, even though if the true difference does not exist, it's likely going to report true difference, even though there's no difference. Therefore, we need a method that will be highly conservative. Then we use SCEFI. Now, do you now know where we use SCEFI now, right? Okay, I'm now going to be showing you some stuff. Okay, I'm going to, now, this is the protected least significant difference that we always do that look like a t-test. You know, the one I said does not really control the family-wise error rates. You know, when we use that, you know, that's likely going to be, you know, kind of issue, but it's now being protected. Initially, it was LSD t-test, but now we have a, you know, Fisher in 1935, you know, actually modify that the conventional t-test that we're supposed to use, okay, in a way, it controls the weak experimental wise error rates. And of course, this method should only be used when you already have a significant result. Now, this is Befferoni. You know what I was trying to do here? If I actually have 3 tests and I want to use it 0.05, the Befferoni says I should divide by the number of possible arrangement. That's why instead of me to use 0.05, okay, because I have 3 comparison, I'm actually going to use 0.0167. So the idea of Befferoni is for you to divide your your conventional level of significance by the possible numbers of tests, and that's exactly what I'm trying to show you. And why do we know it worked? Great. If I plug in the 0.01167 into that formula, what I'm actually going to have at the end of the day, it will recover the 0.05. That's how I know it's going to work. Great. Okay, this is so the idea behind Befferoni is okay, divide your level of significance by the number of comparison. Now, I can now construct a confidence interval based on Befferoni. Oh my God, this is a formula. The correct assignment that I gave yesterday, I needed to pay attention to instruction. There are some that you're going to compute by hand. I stated that. And there are some you're going to use arrow code. So follow instruction. Does that make sense? When I say compute by hand, I need you to show me your formula. When I say use arrow code, I don't necessarily need your code. What I need is your results. Okay, now take a look at this is and don't forget the MSE, the mean square error, you can get it from the ANOVA result. Okay, which is basically going to be the mean square within. Okay, don't forget that. Now, I just talked about Turkey, and I talk about the difference between Turkey and Befferoni. Let me tell you, in statistical analysis, these two comparison methods are popular, very, very popular. Okay, this is the Turkey confidence interval. I told you it is based on studentized range distribution. Okay. Yeah. And so I wanted to take note, of that. Okay. Now, I think I just explained that. Now, how do we do this in R? I think I just explained some multiple comparison to you now. Some are liberal, some are conservative, right? I just explained. And some, we use them for a special situation, like a donut. When I only want to compare level of treatment with control, only I go for donut. It is mathematically proved and statistically observed. When I'm working with sloping data, you go for SCEFI, because SCEFI is highly conservative. The Snoopy data has a way to mislead. If there's no true difference, it's going to report that. Therefore, we need a method that will be highly conservative on that. And the only method that works on Snoopy data is SCEFI. Okay, now I'm actually going back to the data set, the example we're using the other time, where we are comparing the attractiveness of different type of sandwiches. Attractiveness to hand, right? Okay, let's say the null hypothesis is rejected and we conduct a Turkey test. The code on the board is conducting a Turkey test. Now, of course, you're basically going to have 3 possible comparisons, right? Okay, 3 possible comparisons. The numbers of group is 3. 3 combination 2 is going to be 3. But you need to pay attention to the p-value associated with age. Okay, of course, 0.08468. It means there is no significant difference between PB and VEG. Take a look at that. The difference that exists is between the other two. Here I'm using the p-value. Now, take a look at that number 3. If I want to use a formula method, that is a formula for Turkey. Okay. If I want to use code, that is a code. But do you know at times, I can ask you to use confidence interval for Turkey to judge whether significant difference exists. Let us see now. Look at the first comparison. It is from negative to negative, negative 30.09 to negative 0.4067. There's something I wanted to know. When you have from a negative to negative, 0 does not lies, it means there's no significant. It means there is a significant difference. But where you are from negative to positive, 0 lies, there's no significant there. Oh my God. When you take a look at the last comparison, the Vegemite and the peanut butter, you're basically going to see the lower endpoint is negative 18.09. The upper endpoint is 11.5933. Of course, 0 lies in between. When a zero lies in between, it means there's no significant difference. Oh my God, that also confirm the p-value. Look at the p-value. That there's an agreement now between the two. Any question? Because I can give you a confidence, or what if I give you an interval and I actually want you to take a decision using the interval? Okay. If I want to look at the graph, they talk a graph. Oh my God. Take a look at the zero. Did you see the vertical line that corresponds to zero? You see the vertical line, right? Which of the comparison lies that zero lies? Is the last one. Look at the bottom one. The bottom one is the one that falls in zero, where zero falls, right? That is what that graph is telling you. It's giving you the same information, just like what you see here, where you have from negative to positive, where zero lies, where the p-value is large. Okay, so take a look at that. Now we have other useful multiple comparison. I just talked about donuts, right? If your purpose is to compare, maybe you are looking at the effect of mitigation in frustrating or discouraging the spread of a disease, and you have different kind of intervention. You now want to compare each intervention with a control. Oh, I want to compare what is the infection rate. Is the infection rate the same when I use face mask and when I do nothing? Or when I get vaccinated, or I do nothing? Or when I actually do social distancing and when I do nothing? If I want to compare the level of treatment with a control, I go for donuts. This is mathematically proved and statistically observed. Donuts work better than other method of multiple comparison when it comes to comparing control with the other level of treatment. I'm just giving you the code here. Okay, so take a look at that. That is the code. Okay, look at the advantage. Most powerful procedure to compare each treatment to the control. But what is the disadvantage? Oh my God. The disadvantage of the donut is that you cannot use it for other comparison. Like maybe you want to compare, oh, when I wear face masks and or somebody get vaccinated, and I want to compare the infection rate, you can't use donut for that. It has to be purely control on the other level of treatment. That is disadvantage. Now, want to go to SCFE now. Oh, when do we use SCFE? For data snooping. I told you the data snooping is when there is high tendency for you to fabricate false discovery, false positive. Therefore, the SCFE has actually been developed to handle that. Advantage is that the comparison do not have to be pre-specified. But the only disadvantage it has is low power, making it difficult to find differences. Why do we use it in the first place? Because it's highly conservative. So this is the code. Okay, that's the code. Now, where to correct for multiple testing? Don't correct when you do exploratory analysis, and when you generate hypothesis, where this generate many hits, much more, many false, false positives. What we do in statistical analysis, we exploit our data the same way when a patient visits a clinic, the doctor will not start treatment immediately. The doctor is going to do some tests, right? That's what we call diagnostic testing. They do that to understand their patient. We do that in statistical analysis. We call it descriptive analysis. We basically want to understand our data set. That's what we call exploratory data analysis. We control for false discovery rates. That's less than 10%. Then we control the strong family rate, typically at less than 5%. This is the remarks. There's no agreement as to the best procedure to employ. Think about the different RA and decide which is the best for your situation. Keep in mind, there's going to be a trade-off between type 1 and type 2. Let me tell you, when you try to minimize type 1 error, you cannot minimize both types of error at the same time. When you minimize type 1 error, type 2 error is going to go up. But you can always strike a trade-off between them. More stringent procedure mean it is more difficult to reject. When I say more stringent procedure, more difficult to reject means you are actually having procedure that is highly conservative. Okay, where you always go for the null hypothesis. Okay, I'm more likely to miss some differences that do exist, because if differences exist and you are using highly conservative procedure, even if the nature says different exists, you will not be able to detect the difference. And in that situation, it means your tests have low power. Let me tell you this. The reason why we normally record error because of the low power, low statistical power. What can we do to have a high statistical power? Maybe more data or more sample size. But don't forget, we are limited by budget. How are we going to do it? Some of the procedure are only valid if the comparison were pre-planned and not suggested by the data. Where they are pre-planned, like the contrast that we did last week. But the one suggested by the data is when you are just like considering possible comparison. And the last one, we said, other procedure like SCFI allow for data snooping, and this step possess low power with high type 2 error, making it hard to find differences. The last one, when possible, use procedure that best answer the research question. I know before you go into research, you have a certain question that you basically want to answer, right? Then use, for instance, maybe before going to my research, what I have in mind is just to compare the control with the other level of the treatment. Then I will go for donut. But if I'm not, then to choose between Turkey, Bufferoni, and others, that now depends. And I said, for example, use donut test to compare each treatment to the control. Oh my God, this is the last slide. And what are we going to do next? Two-way analysis of variance, which means we're done with the one way. But let me tell you, in the exam, you are not going to have, there's not going to be a question from what we're going to start from Wednesday. If you look at the midterm 1 practice question that I released, it covers all the way to today. So the two-way ANOVA will not be part of midterm 1, what we're going to start on Wednesday. Do you know that by now, you can confidently go back to the midterm 1 practice question? We've already covered everything in that midterm 1. Look at the example. But you know what? We're going to dedicate a class where we're going to go over those questions together. You can now see in statistical analysis, we don't just choose technique. There's a reason why we choose whatever technique we choose. There's always story behind all our activity. Any question before I go today? Any question? I think I'm beginning to have confidence with students in this class with the way you guys have been responding to my questions, with the way you ask questions. So I now believe that some of you are getting the information that I'm passing across. But if there's anyone among you who is struggling, please reach out to me. I wish you the best. Make sure you stay safe. Have a lovely day. Bye for now, everyone. Oh, the guy online, don't forget to send me a message for extra credits. Okay, good job for sharing that. Bye for now.